Hi, and welcome to our first actual lesson of calculus. So this is the beginning of our actual material that we're going to be covering. We're going to start this chapter talking about limits. That's going to be our main focus, something that we're going to see a lot in calculus. The idea is that we're interested about where a function is going. Sometimes a function may not necessarily reach a particular thing, but we care about like what's the direction that it's going. They can reach a number, or they might kind of go to nothing. They can eventually, we'll see later, they can go to infinity. So they can just keep going and becoming larger and larger, or they become smaller and smaller. Eventually, they're going to hopefully hit some sort of number. Otherwise, they might not exist. There's a couple examples that we want to be careful of. So you might want to pause the screen here so you can write all this down and then resume the video. But we care about functions being nice. So something like x being squared, that's something that's nice. So there's no real trouble there. So that will get us nice limits. We do worry about things where you get 0 in the denominator, we get holes in the graphs there. That can cause a problem with our limit in some sense, but we can still actually find a limit. Like even though we can't put a 5 here, this still does tend towards 14. It doesn't quite get towards 14, but that's where it's kind of going. It can also jump from one thing to another thing. So here we're jumping from 3 to 1. And if we're at -2, the limit doesn't exist, because if it's going from one way, it's getting to 3. And if it's going from another way, it's going to -2. So it's not going to a particular thing. Also, if there's like reciprocal functions where they kind of zoop up in opposite ways, kind of like we had that 3 and the 1 where they weren't quite matching up, they swoop away from each other, the limit's not really going to anything in particular. So let's find a couple of these. In our first example, I've got another one where it's kind of like split, where it's not quite meaning the same thing. Now you'll notice that there's this little tiny notation. Here there's a minus, here there's a plus, and here there's nothing. So these are one-sided limits. This is talking about what's x doing as it approaches 3 from the left. So this is from the left. This is what's happening to x as it's approaching 3 from the right. So this one, if we were to start with that, which would make sense because it's a, is what's happening when it's approaching from the left. So what's it doing as it moves along that line? Well, as it moves along that line, it seems to be staying at the same number. So it's kind of been at the same number, still staying at the same number. So it's staying at, let's see, this is 1, 2, 3. So this limit, as it's approaching from the left, is 3. But with the other one, this one, as it's approaching from the right, so it's moving this way along the line, we're sticking at -2 the whole time. So coming from the right-hand side, the limit is -2. Since those aren't meeting at the same thing, since they don't match up, there is no limit. So in this case, the limit does not exist. We want them to like be tending towards the same thing. Both the left and the right are meeting at the same spot. We got a nice limit. Since these don't match, this limit does not exist. However, f of 3 does still exist. We can see it. It's right there. Look at it. There it is. It's that little dot. It's even actually something else. 1. Yeah. Let's take a look at another example. Here we got secant. So in order to figure out if this limit exists, we got to check it from the right and from the left. I don't know if I've got my left and rights correct, but we want to see what's happening as we move along the graph in both directions. As we move along the graph this way, it's heading towards 1. Okay. As we move along the graph in the opposite direction, we're just checking at 0. As it's tending towards that 0 right here, both directions seem to be heading towards 1. Since they're both heading to the same value, we do have a good limit, and this limit equals 1. So they meet, got a nice limit. Now some weird stuff happens. Check this out. If we do this one, once again, we got to check the left and we got to check the right, and we got to see if they meet in the same spot. As I'm moving along here in this direction, the graph, as it's going towards this 1, here's our 1, it's heading towards 4. But it doesn't actually reach 4. When it gets to 4, it suddenly jumps down there. But we don't care about what happens at 1. We care about what's happening as it's going towards 1. We don't care about what happens right there at this moment. When we're checking that left-hand limit, we only care about where is it going towards before it gets there, as it gets closer and closer and closer. As this gets closer and closer and closer to 1 from the right-hand side, it is also heading towards 4. Since those match, this limit does exist, and its limit is 4, which is interesting because f of 1 isn't 4, it's actually 2. So the limit in the value of the function doesn't have to match. It can, that'll happen sometimes, but then there's other times where the limit of the function at the particular value that we're working towards don't match up. And that's perfectly fine, they don't have to. All right, let's use these limits to kind of get an idea of which of these tables might be. Like we could put these into a graph and figure it out, but let's use our idea of what this limit is doing. So we know we're gonna have a hole in the graph at 1. We're gonna have some trouble there. So at 1, we should see a little hole, a little error. And we see that in all but this one. Here, 1 works out. So we know it's definitely not that one. But in all the other ones, we've got a nice error, which is good because we can't divide by 0. So good, error. As we move along the graph this way from the left-hand side, the limit is increasing. So as we move along the graph, it is getting bigger and bigger and bigger. So before that error, we should see this number getting bigger and bigger and bigger. So if we check this one, yeah, good, it's getting bigger. We check this one, yeah, good, it's getting bigger. We check this one, yeah, it's getting bigger, I think. Yeah, yeah. If we check the other direction, whoop, here it should be getting smaller. So this is getting smaller, this is getting smaller, and this is getting smaller. But what is that limit heading towards? Well, on this side, our limit is 3. And on this side, our limit is 3. So the limit's going to help us out figure out like which one it's going to be, because it should be heading towards 3 as it moves closer towards that error spot. It should be aiming towards 3. And the one that's doing that is this one. This one is getting smaller towards 3. This one is also getting smaller towards 3. The other two are not heading towards 3, so that's not our graph. This is our good one. So it should be that one right there. All right, so I've already drawn the graph of f, so I've done this in Desmos. If you want to see what the Desmos graph looks like, I've actually put the URL down here. You just go to desmos.com calculator and then type this little bit of garbage at the end. So we want to care about where is the limit going to exist. So where are we going to have that nice spot? So we're looking for holes. Ooh, here's a hole and a jump. That's kind of like double trouble right there. Everywhere else, we're fine along the graph. However, we're not good right there, and we're not good right there. At that point, when we come in this way, we have a limit. But when we're coming in this way, there is no limit there because the graph doesn't even exist, so we don't really know what it's doing. It happens in reverse in the other one. This way, we have a good limit. It's heading towards something. But when we come in on the other direction, we don't have a graph, so we don't have a limit at those points. So when we state our interval, we want to say, hey, well, we're not okay at -2, but we're kind of okay like right after it. So -2 pi, I should say. We do have some trouble though once we reach 0. There's trouble brewing right here. So we need to skip over 0 and then continue on afterwards. So right after 0, and we can keep going to 2 pi. But again, at 2 pi, at that very end point, sure, we've got a nice point there. It's not that it's a hole, that's filled in. But we don't have anything on the other side. We got something coming up one side, but we don't have anything on the other side. I don't know if my hands are correct there, but you got one side, but not the other. But we do have what they're looking for here, where the left-hand limit exists or the right-hand limit exists. So in this one right here, we've got stuff on the right-hand side, but we don't have stuff on the left-hand side. So at this point, we have a right-hand limit. So the right-hand limit is where c equals 2 pi. Negative 2 pi, I'm sorry. I might say positive 2 pi. Then we have a left-hand limit on this side, the red part, but the orange one's not quite working out very well for us. So on that point, we have a left-hand limit. Now, I've been saying this earlier, but hopefully you're not writing you're writing all of this. All you're writing is Finney, page 65, number 61. You're gonna write A, B, C, D, and then just answer this stuff. Make a little rough graph. It doesn't have to be perfect. We're gonna do one more of these. So we're looking for our scary spots. So we've got a big scary spot right there, big trouble. We've got our same problems over here, same problems over here. Now you might be concerned about this spot right here. At that point, it seems like, we might have a jump in the graph because that's how the other ones have worked, where we've moved from one thing to another. However, the way these two functions are lined up, they actually meet very perfectly. So as we're coming up in this direction, this one's tending towards 0, and the other one's tending towards 0. They're both heading towards 0. Sure, they're getting there in a little goofy way, but they're both heading towards 0. So we will have a nice limit. So where the function does have a nice limit is from negative infinity. We don't, sorry, it starts at negative infinity because note that this one doesn't have, so it's x is less than 0. There's a little arrow. This thing keeps going. There's a little arrow. This thing keeps going. So we don't have that trouble. No trouble this time. The only trouble is this spot. The previous example was stopping. This one's not. So negative infinity, and then we keep going until pi. That's where we run into trouble. Kitty cat. Been hearing her zip around in the background while I've been talking to infinity. So we just have that one gap because again, this one, it's got the arrows, so it's going to keep going. In our previous example, x was being limited, so it stopped right here. And then x was stopping at 2 pi. However, the one we just did, this one keeps going. Sure, the middle piece is being limited, but the other ones, they keep going. So that's it for limits for today. Thing to keep in mind is that you want to check if it's nice. Are there holes? Do we jump? And is there asymptotes? And we're going to see those asymptotes a little bit later. But the important thing, if you've got a nice limit, you have to make sure both the right and the left meet up. If they don't meet up, then your limit does not exist. That's it for limits. See you later.